Welcome. This is now video number 8 on the construction of hyperreal numbers. We are here going to start with hyperpairs. I am using notes that I believe I got from the book of Nigel Kirtland. However, this book is at the office, which I cannot access right now because of the lockdown, so I'm not 100% sure these are where my notes are coming from. Let us consider a pair of elements A and B inside the Cartesian product of the two sets xn, yn. We can build a sequence of pairs and we can build an equivalence class of this sequence. With every element an and bn, we can build two hyperreal numbers. And with the sets xn and yn, we can build the hyperset curly x and curly y. Our goal is to see if the hyperpairs constructed as an equivalent class of a sequence of pair can be mapped onto a pair of hyperreal numbers. We are going to say that two sequences of pairs are equivalent if and only if the pairs are identical almost everywhere. And we define S as the equivalence class of a sequence. If one can show that every equivalence class of pairs maps on only one pair of hyperreal, then we will have shown that S maps on the Cartesian product of the two hypersets. The set of integers for which the pair are identical is given by the intersection of the two sets of integers in which an equals cn and bn equals dn. Remembering the properties of a filter, we show that the sequence A is equivalent to the sequence C and sequence B is equivalent to sequence D if and only if the sequences of pairs are equivalent. We can write the equivalent class of sequences of pairs, and if we wish we can rewrite it explicitly using the hyperreal numbers A and B. Let me now define the map M, which takes equivalence classes of sequence of pairs, which are elements of the set S, and give us pairs of hyperreal numbers AB, which belong to the cross product of the two hypersets. We can easily show that the map M is surjective as well as injective. I'll let you look at those few lines if you need. And this allows us to conclude that every hyperpair created as the equivalence class of a sequence of a pair of real numbers maps to one pair of hyperreal number, curly A, curly B, and inversely. And in particular, the extension of a pair xy is simply the pair given by the upper star x, upper star y. Let us now define hyperfunctions by using the same method. So we define fn, a function from xn to yn, both being xn and yn being subset of R. And we define capital F from big X to big Y, big X being defined here, big Y is here, where capital F is defined as a sequence of functions, f1 being defined between x1 and y1, and fn being defined between xn and yn. Let A be a sequence of real number, and we write f acting on A as the sequence which is defined here. And finally, we say that two sequence of functions, capital F and capital G, are equivalent if and only if For all A and B sequences which are equivalent, we have f of A equivalent to g of B. The hyperfunction, which we are going to write curly f, is defined as the equivalence class of the sequence f. And we say that curly f is a function acting from the hyperset curly x to the hyperset curly y. And finally, all functions which can be created like this using the same process are called internal functions. As always, we have special notations when we want to talk about constant sequences. The conventional notation is star f, which you will find in most books or lecture notes. However, I prefer to use this notation here, and I will try not to use that notation. So using the notation I propose here, let us see what this object is going to be. It is given by the equivalence class of the constant sequence of function f acting on the constant sequence x, which by definition is the constant sequence of the real number f of x, which we can write as upper star f of x. I can now remove the brackets without creating confusion, and you may remember the relation we had seen before, where lower star upper star on x is equal to x. And we see that we have something very similar here, where the lower and upper star can be removed. Let us consider the hypernumber A given here. If I look at this object, the best I can do if I don't have more information about the function f is to write the equivalence class of this sequence. It may be the extension of a real number, but it may also be a purely hyperreal number. If you choose to use the conventional notation, you need to be a bit careful, as the symbol star f of x could be understood as this or that. The two are of course identical if x is the extension of a real number. But as I said, I am not going to use this notation, and I'm going to try to stick to that notation here. Finally, we can define the shadow of a function f. We write it circle f. It takes an element of a hyperset, curly x, and gives us a real number. It is defined as the shadow acting on the hyperreal f of a. And in particular, if f is the extension of a real function, then you can show that circle f acting on star x is simply f of x. Let us build an example. Let f be a function from R to R, which maps A to A over n. The sequence fa is therefore given by this guy here, and I can rewrite this as a product of two sequences. And it's then easy to see that the hyperfunction f is simply the function which divides by the unlimited number curly n, or if you prefer, the function which multiplies by the infinitesimal number epsilon. We have another example with the function g, which acts on a pair of numbers n and a to give us a over n. This time, let us define the extension of g by building the equivalence class of the constant sequence. This function takes element in the extension of the cross product nr, which we have seen to be in fact the same as the cross product of the extension of the two hypersets. We can write the extension of g acting on two hyperreal numbers k and a, And in particular, if we take K to be now the well-known curly n, then we see that the extension of G acting on curly n and curly A is equal to f of A as defined in the previous slide. We should be a bit careful about the contraction of the lower and upper star. It is only when all variables are the extension of real number that the function simplifies, allowing us to write this as if all upper stars contracted with the lower star.